Welcome back to the course entitled Elementary Electrochemistry. In the previous lectures, we have discussed about the EMF and its relationship with equilibrium constant, and we have discussed about the Nernst equation, how it is formed and how one can use it. And then towards the end of the last lecture, we started discussing about different types of half cells, and in that we first discussed about the metal ion electrodes, and we gave some examples of metal ion electrodes towards the end of the previous lecture. So now I would like to discuss the second type of electrodes, the gas electrodes. So you can easily understand that from the name of this electrode, one of the component of this electrode is a gas. So in this case, a non-metallic element is combined with an inert metal to form the electrode, and this non-metallic element is in general a gas. This combination of a gaseous non-metal or gaseous, I would say, a gaseous element like hydrogen, chlorine, etc., with an inert metal like platinum forms a particular electrode which we call as the gas electrode. So when you have a platinum electrode and hydrogen gas is bubbled around the electrode, that electrode is written as H2. Platinum is the electrode, is in equilibrium with H plus. So this is the electrode. Or a chloride anion is in contact with chlorine gas with a platinum iridium alloy used as an electrode. So in this case, the reaction is H plus taking up one electron is giving you hydrogen. Similarly, half Cl2 is taking up one electron giving you Cl minus. So this is the cell reaction in reduction direction. Okay, just to remind you once again, the cell EMF or the half cell potential of this hydrogen platinum electrode E0 half H2 to H plus is taken as 0, the standard, and based on this value of half cell potential of this reaction, all other cells are determined, their corresponding EMF is determined based on the value for this cell taken as 0. The next type of single electrode is metal and sparingly soluble salt electrode. So in this case, we take a metal and its sparingly soluble salt in equilibrium with a solution having the same common anion, as that of the sparingly soluble salt. So some examples are like this. Silver is the metal, the corresponding sparingly soluble salt is AgCl, which is in a solid, and you take a solution of KCl in water where the anion is common. Similarly, one can use mercury, Ag2Cl2, solid with KCl aqueous, or Pb with PbSO4, solid with K2SO4 aqueous. So, just I am writing one of the cell reactions. So, for this half cell reaction, you will have a set of two reactions. Ag solid comes in equilibrium with Ag plus electron, and then this Ag plus reacts with a Cl minus from the solution and forms AgCl solid. So the overall half cell reaction is Ag solid, that is the metal, taking out Cl minus from solution which comes from KCl, is in equilibrium with AgCl solid plus electron, right? So this is a reversible electrode with respect to chloride ions. So for your practice, you try to write down the half cell reactions for the other two cells which I have indicated here. So those will help you understand how to write the half cell reactions and join them and write the complete half cell reaction. The next type of half cell is the oxidation reduction electrode. Here you may ask one question, that why suddenly this electrode is called just the oxidation reduction electrode, while all the previous reactions involved oxidation and reduction. See, if you have noted, or if you have noticed the cell reactions, whatever we have written in the previous cases of metal ion electrode, metal sparingly soluble electrode, gas electrode, everywhere we have talked about the oxidation and reduction process involving the particular element in its elemental state, that is oxidation state 0. Hydrogen electrode, chlorine electrode, and then metal ion electrode. Everywhere the one of the element is taken at its oxidation state 0. So in this case, we have a slight difference here, and inert metal like platinum is used as an electrode with a solution in which the components undergo oxidation or reduction. So here we should have a solution in which we should have some elements in its lower and higher oxidation state, and during the half cell reaction, the lower oxidation state can go to higher oxidation state can come to lower oxidation state, and if such reaction happens with a platinum electrode, we then call it as oxidation reduction electrode. Remember, here the elements which are undergoing oxidation and reduction are not used as in its elemental state in these cells. So such examples are like this: Fe2 plus Fe3 plus electrode, Sn2 plus Sn4 plus electrode, stani, or hydroquinone quinone electrodes. So in this case, the iron 2 plus is in equilibrium with iron 3 plus electron. Similarly, Sn2 plus is in equilibrium with Sn4 plus 2 electrons. And as you know, hydroquinone is an organic compound with OH group on 1 and 4 position of aromatic ring, the benzene ring, is in equilibrium with this ketone or diketone, which is called the quinone, and it releases 2H plus 2 electrons. So in general, one can write it as reductant is in equilibrium with oxidant plus n number of electrons, that is the difference in their charge. So now, if you remember a Daniell cell where we had zinc and copper as electrodes, those represent a cell where one uses the metal ion as electrode. So in Daniell cell, when we get electricity out of it, then Zn gets oxidized to Zn2 plus, that is metal-metal ion electrode, and copper 2 plus gets reduced to metallic copper and acts as cathode. So this cell reaction is written as Zn plus Cu2 plus giving you Zn2 plus Cu. So here this is oxidation, this is reduction. So if you try to write this cell in one line, one should write the negative electrode, that is the anode on the left hand side, which is Zn in equilibrium with ZnSO4 aqueous, and it is kept in isolation but through a connection, which I will explain what does that mean in a future lecture. Copper sulfate aqueous in connection with metallic copper, which serves as the cathode, the positive electrode. So what one can do using these electrodes is the following. So what you do is you take one of the electrodes and we name it as electrode 1, and the second electrode and name it as electrode 2. These two electrodes can be anything irrespective of the nature of those electrodes. So one of the electrode can be, suppose, a metal ion electrode, and the other electrode can be a redox electrode, which can be coupled together to form a cell. So what one has to do is, individually one has to know the E0 value in the reduction mode for this cell and the E0 reduction mode for that cell. So then you compare the values, physical values of these two half cells, and if suppose E0 value for this half cell is greater than that, then one has to form the cell in such a way that the reaction metal ion to metal takes place in that particular cell. That means Mn plus should get reduced to a metal releasing n number of electrons. And where does reduction takes place? Where does the reduction takes place? If you go back to my previous slide, you see the reduction is here, that is copper is getting reduced, and the reduction has taken place at cathode, and oxidation is taking place at anode. So then if we encounter a situation like this where electrode 1 has higher reduction potential compared to electrode 2, then the corresponding cell that one has to form should have electrode 2 on left hand side, which will then be anode. It will be connected to the electrode 1, which will serve as the cathode. So here in electrode 1, you will encounter the reduction of the metal ion to the corresponding metal, releasing n number of electrons, whereas in this electrode 2, some other metal M prime will get oxidized from its, say, N plus state to M prime N plus N oxidation state by releasing N number of electrons, right? So I think this may not be a very clear representation if we assume that this redox electrode is a ferrospheric system. So then at this electrode oxidation will take place. So Fe2 plus will release electrons at the electrode and will get oxidized to Fe3 plus. So this is the oxidation and this is the reduction that will take place. Now you see this electrode 2 is a metal ion electrode. So here you have to have, in addition to electrode 2, a platinum which is used to conduct electricity. So you have to apply platinum as the electrode metal, and the corresponding electrode reaction is happening between ferrous and ferric. If you go back here, you can also see that we said we will have to use the inert element platinum as an electrode to do the electrical connectivity, and that electrical connectivity will enable you to do this reaction in the cell, right? So with this I would like to conclude this lecture, and from this point we will continue in the next class. Thank you.